Welcome back, everyone. In this episode, we'll be taking a look at KProbes or kernel probes, and we're going to be using them to overcome some of the limitations we faced in our previous application with the trace point. So this is what we're going to be building real quick. Um, if I was to perform a curl on google.com at this point, along with the fact that it logs that a kprobe with an IPv4 address has been called, it logs the IPv4 address as well. So if you remember in the previous episode, the only features we had access to was the file descriptor number and a couple other pointers and whatnot, but we weren't actually able to dereference the pointer and get the data that was that's placed in the structure that's referenced by that pointer, right? So that is what we're trying to overcome in this with the use of KProbes, and we'll take a look at how that can be achieved. So we're going to be placing a kprobe on the TCP underscore connect function in the kernel, and you can place kprobes anywhere in the kernel. It's all up to you. You can place kprobes or kret probes or kreturn probes as well, which will be called whenever a function returns. In here, we're calling the kprobe at the entry point of the function. So if we take a quick look at the documentation in the Linux, if we in the Linux source code, you can see that it takes a structure, which is a socket, and we're going to take a look at how we can extract the data out of the socket. So anywho, let's get started right away, and we'll create our new Rust project to actually get building. As usual, this is going to be an implementation heavy video. So I'll have checkpoints and chapters listed in the description below if you want to skip forward or go back and watch it at your own pace. So let's copy our generation, the snippet we use for generating our code, and paste that in. I'm going to call this TCP underscore kprobe. And the type of program that we're building is a kprobe. Now it's going to ask me which point I want to attach this kprobe at, and that's going to be a TCP connect. Great, so it's created my project. Let's open that up in Rust Rover. Kprobe. And we'll take a look at some of the boilerplate code that Aya has generated for us. So while that happens, I'm going to start running the compiler so that by the time we look through the code, it has built some of the artifacts and cached them. Anywho, so if we take a look at the KProbe eBPF part of the application, there's not much to it. It's the same thing that we had done with the trace point. The only difference here is that instead of this macro being a trace point macro, it's calling a kprobe. And in here in the probe, we're getting a probe context, whereas in the case of a trace point, we would have gotten a trace point context. So there's a few differences with the probe context. We'll take a look at how that works as well. And then finally, we've got the TCP kprobe, the user space application. And the only difference here is the program type is going to be a kprobe instead of a trace point, and it loads it at the attachment point that we had asked for it to attach itself to. Let's see if the compile process is complete. I think it's almost done, just in time. So I'm going to enter my password real quick. Great. Now that that's running, I'm going to perform a curl, and you can see that we are at the same point that we were at in our previous application with the trace point, where we had the we were essentially logging whenever a TCP connection is being created. All right, so let's take a look at the context object that we have and what we can do with it. So in the context object, we've got a new method. Obviously, that's just a constructor. Then we've got the arg constructor, I mean the arg function, and this essentially lets us extract any argument depending on the index. So if you've got a method that has 10 arguments, you would use the indexes appropriately. In here, we've only got one argument, so we're going to extract the first one. If you want to take a look at how this actually works, so the way it works is you've got specific registers that are used to point towards the memory location for arguments. So for example, if I go into the Linux document, into the man syscall, You can see that the syscall library has specific definitions. So depending on your architecture, the system call number uh, will be placed on a certain register in your processor, and the return value will be obtained in another register. Along with that, we've got definitions of where we can place arguments. So for example, in the case of x86-64, you will place your first argument in RDI, then in RSI, then RDX, R10, and so on and so forth. So this is what is used for actually defining our arguments, and you can see that those match up right here. So if I take a look at the from argument method, we've got RDI, RSI, RDX, RCX, the same way that it was listed out in the documentation. So this is a fun little exercise to understand how syscalls work. So essentially in each of these registers, you will place the pointer that's pointing to your argument. So for example, in the case of the first argument, you will place the memory location of of the value of your first argument essentially into your register. Okay, so now that we've got that out of the way, let's take a look at how we can extract all of this. I can simply get access to all of this data from ctx. So I'll just call it let arg equals ctx.get.arg, and that's going to be a 0. I believe it has to be unwrapped. Let's take a look. It's an option. Yes. So I'm going to unwrap that. Awesome. So now we've got the, or instead of unwrapping, let's just, yeah, I think unwrapping is fine. Cool. So now we've got the first argument, and we can take a look at how we can extract the data that we need. So if we take a quick look at the structure definition that's present here, so the TCP connect method is going to be called with a sock structure. And let's take a look at the definition for our socket. It's defined, it's documented in here. It's defined, I believe, in here. Yes. So this is a long documentation for it, and it begins with a structure called a sock common. Let's take a look at that. So while we're looking into this documentation, there are two approaches. So one approach is where we build our own binding of the structure to the Rust code. And there's another approach where we use certain automation tools that will generate all of this for us. So we're going to go through both of those applications, and we're going to take a look at how both of those can be achieved. So now we've got the definition of the sock common as well as the sock.h. Cool. So let's work towards chipping away at actually building this. I'm going to define a structure called sock, and this is going to have a sk underscore common, which will be a sock common, and we're going to define sock common as well. Let's make these public because we'll need that. Okay, so if we look into the structure of the sock common, we've got a union at the beginning, which is an adder pair, which is really just two 32-bit integers. One is the destination address, and the second is the source address. So let's do that. We're going to call it DADDR, which is going to be a U8 of 4 bytes, because that brings it up to 32 bytes, which is which is the number of bytes that an IPv4 address is. We're covering this for IPv4 for now. We'll take a look at IPv6 shortly. The definitions for IPv6 are are way far down over here, so we're going to take a look at that eventually. So let's do sadder is also going to be a U8, and these will both be public because we need to modify them as and when we wish. Cool. Now that we've got the definitions here, we're going to have to let Rust know to represent them in C, in the format that C does, because the kernel is using the C representation. So obviously we have to use a C representation as well. So we're going to use a macro for that called the repr macro. And that essentially lets Rust know to store this in memory the same way that it would store a C structure. Cool. So we've got our sock common, we've got all of this. Let's work towards extracting the data out of this. So real quick, actually, before that, let's work towards getting the ports as well, the source and destination ports. So if we take a look at the definition, we've got one block of memory, which is this is what 32 bytes long. And then right after that, we've got our ports. So this is the data that we want to take. So we need to skip over these 32 bits of data, and we need to access this data. So let's take a look at how we can achieve that. All I've got to do is come back into my code, and I can essentially just label this as ignored, and this is going to be a U32 because it's 32 bits of data. It could be, I could label it as a U8 comma like semicolon 4 as well, because the only thing that I need to achieve out of this is to skip 8 bytes of data. So I can do that just as well. And I've got an skc underscore, let's just call it what it's called in the documentation. So real quick, let's just to maintain consistency, we're going to call this skc underscore deadder, and same with the receive, it's an skc underscore rcv underscore source adder. Then we've got the ignored bits. Then we've got our destination port, and I believe this is, I'm not really sure what this is, but this is a destination port. So let's bring that in, pub skc underscore d port. That is going to be a U16, right? After that, let's take a look at the documentation real quick. skc underscore num. This is the placeholder for the inet num. Not really sure what that means, but we're going to ignore that for now. Cool. We've got the family after that. So the family essentially lets you know if it's an IPv4 connection or an IPv6 connection. For now, we're going to skip over this. We'll take a look at this when we deal with IPv6. Right. So let's dereference this pointer that we had taken over here as a socket, right? That's what we aim to achieve here. Now, one problem that I will have right now is if I compile this application, it's going to fail. So let's do that. Right. So it fails with the let's see, type must be known at this point. So it's essentially telling me that you have to let me know what is the type of this argument. So let's assign it a type. This is going to be a pointer to the first element of it's going to be a pointer to the socket structure. So if we look at the definition of the TCP connect once again, you can see that it's a pointer to the socket structure. So let's do that once again. Let's let Rust know of that. So I'm going to call it a const sock. So now that Rust knows that it's a pointer to the socket, it will stop yelling at us, but it's going to throw another error very shortly if you take a look. So it tells me that the last instruction is not an exit or a jump. The reason behind that is when this unwrap fails, it's going to throw a panic. And as soon as it throws a panic, the panic handler is going to get triggered, which is defined here. The panic handler is a loop. And like we had discussed earlier, the verifier has to be able to verify deterministically that your application will not be stuck in a loop indefinitely. So we cannot let our application panic here. This is one of the advantages of eBPF because it essentially stops you from shooting yourself in the foot at any step of the way. So we need to change this into an or else. For now, I'll just call it in, I'll just label it as I underscore U32. And oh, sorry, it's going to be an OK or. I'm just going to throw an error upwards, and the try probe method is going to catch that. Great. So now we've got the pointer to our argument. Let's call it a sock pointer now that we are getting our bearings a little bit. Now let's dereference this into our socket. So it's fairly straightforward. It's going to be an unsafe function because you are referencing raw memory. Uh, Before that, let's just try compiling this. Okay, so that works out. Now that we've got our socket, let's move forward and let's try to extract our sock common out of this. So let sock underscore common equals sock underscore sk common, sock dot sk underscore common, and it's not going to let me do that. So the reason here being I need a reference. Let's do that. Cool. So let's just try printing the same logger that we did earlier along with, let's just do an sock underscore common dot let's just do skc destination adder, and this is going to be an IP address, so let's add that. Cool. Let's take a look at what happens when we compile. So it's denied us permission, and the reason being that we're performing an invalid memory access on a scalar. What does this really mean? Well, you see, the problem here is we're behaving as if we have access to all of the memory. As an eBPF program, you are running in a virtual machine in the kernel space, albeit, but you don't have access to all of the memory as if it was yours. You have to call some helper functions on the you have to call some eBPF helper functions to actually get access to the memory that's behind this socket pointer. So let's take a look at how we can achieve that. So what we're going to do is we're going to take a look at the documentation with kernel read. I believe it's in the, oh, sorry, docs.rs. Let's do a kernel. I think it's a read underscore kernel. Yeah. So if we take a look at this, we've got the helper read kernel, and it essentially reads, you have to give it a size depending on the size of the object you're trying to read, and it essentially reads that amount of memory out of the kernel, so out of the kernel memory. So let's take a look at how we can achieve that here. What I'm going to do here is, instead of calling this instead of directly dereferencing the pointer here, we're going to assign a bunch of memory on the stack of the eBPF application, and it's going to be zeroed. Obviously it needs a type hint to decide what kind of data that's going to be storing. So this is going to be a sock. Great. So now that we've got this going, let's actually dereference the memory that's present in this pointer. So that is going to be an unsafe action again, and we are going to call our method that we had referenced here, bpf probe read kernel. So it's a bpf probe read kernel. Cool. Now we give it the pointer that we had earlier. So the pointer is a sock pointer, and we have to provide this to the kernel, and then we have to let it know where we want to where we want it to essentially extract the data into. So let's do that as well. So actually this is not going to be an error, this is going to be a result. And in here we're going to perform a check where, first off, we have to perform a check if this pointer is empty, obviously, although that won't really be required. Let's just do a result. Let's see, result dot is error. If it's an error, we're just going to return from here, and if it's not, then we can process this into our socket. So let's remove the initialization from here, and in here we are going to call it a sock equals result dot unwrap, not unwrap, but I think Yeah, dot or else. Whoa, it's going to be a result dot map underscore error. And there we go. So we're going to throw uh, 2 as the error if we're not able to actually unwrap this, although this will never happen because we're already performing a check right here. But anywho, let's move forward. So now we've got our sock common as well. Let's do sock underscore common equals sock.sk common. And I think we are good to go. So let's compile this application and see if the compiler yells at us. Perfect, no errors. Let's do a curl to google.com, and we're getting our IPv4 address along with the printout as well. So let's, now that we're here already, let's try printing out the port as well. And that is going to be the sock common dot skc underscore dport. Let's take a look at this. Beautiful. So it gives us an invalid port. The reason being, this is the endianness at play. So we need to convert the endianness of this port into the endianness of our application of our host machine. The port is in big endian format, as uh, all network representation is big endian. We have to convert this into little endian. So let's do that real quick. I'm going to cut this, and we're going to do a U16 from big endian. So this essentially converts your big endian representation into the native endianness of your application of your host machine. So let's do that. And we're getting the right port as well. If I was to perform a curl on HTTPS, we would get the same thing. Now, the interesting fact over here is if I was to perform this on IPv6, I would have a completely different output. So let's do that. Let's do a curl on IPv6 with my loopback address. And as you can see, I'm getting a 0000 with a port 80. So that doesn't really sit well with me because there's something wrong here, right? The reason being that when an IPv6 address is used, the IPv4 part of the socket structure is going to be empty, and is going to be the data that's going to be populated is in the IPv6 part instead. So that's where you're supposed to look into the family. If we go back into the definition, the socket family actually lets you know what kind of an IP address is being referred to over here. So let's take a look at that. We'll add that to our structure, pub skc underscore family. And this is an unsigned short, so U16 is going to be fine. And let's print that as well. That's going to be a sock common deadder dot skc, no, not deadder, skc underscore family. Okay, let's, oh my bad, not in here. Great. So the compiler is not yelling at us. Let's compile all of this again and let's run it. Great. You can see that, okay, 1 second, google.com. The family isn't exactly correct here. So let's, sorry about that. So let's take a look at what's gone wrong. This is part of what's so finicky about C development, and the whole point of all of this being unsafe is that it doesn't really throw a compilation error. Instead, you get these problems at runtime. So the issue here was that if you look at the documentation, there's a couple things we missed. So after the port pair, we've only used the D port, right? There's another 16 bytes of data that we need to ignore yet again. So let's do that real quick. Let's call this ignore 0. We're going to add a pub ignored one, which is another U16. Then we'll have our SKC family again. So let's close all of this and let's run that again. If I go in here and perform a curl on google.com, great. Now I'm getting a family of 2, which is the definition, which is the integer representation for IPv4 addresses. Let's try doing a curl on IPv6 and we get a family of 10. This refers to the positions in, let's see, if I was to go in here and if I was to do a man connect, I believe. Oh, I believe it's a man socket, sorry, man socket. And in here we've got definitions of all of the different types of families that are supported. So you've got 0 at AF Unix, you've got 1 at AF local, and the INET, which is the IPv4 protocol, holds holds the representation of 2. And similarly, INET 6 is going to be a representation of 10. Now, we're still facing this issue where the data isn't really being populated properly. So especially if you look at this field right here, you've got all garbled up sort of data. It's not really accurate. So in order to get the correct IPv6 values, what we're going to have to do is we're going to have to parse all of this data. So the same way that we had serialized this with adding some ignored bits and things like that, all throughout, all the way up until we have the data that we need, which holds the details of the IPv6 address. Obviously, that's a lot of work, and doing that manually is not really sustainable. So luckily, we've got certain tools that Aya provides us that we can use to essentially skip all of this. So if we open up the Aya documentation and go into this page right here, so in working with Aya using Aya tool, it's going to suggest certain places or certain commands where you can generate your kernel bindings. And this is a very useful tool. It has a few requirements. You're going to need to have BPF tool and Bindgen installed on your system. So installing Bindgen is fairly straightforward. As for installing BPF tool, it depends on the distro you're using. For the most part, if you're using Ubuntu or Debian, you can just do a sudo apt-get install BPF tool and you'll get it installed. So let's take a look at how we can use Aya tool to generate this Bindgen tool to generate the structures that we need. From the stuff we were looking into, we needed the socket structure and the socket common structure, right? So let's take a look at how we can get all of that. Let's go into our application, and in here we are going to copy this string right here and we'll change it according to what we want to achieve. Cool. So let's go in here, we'll open up the terminal. I'm going to be pasting this in the common directory of my application. You don't have to paste it in the common directory, mostly because this is something we'll only be using in our eBPF site, so don't really need it, but it's okay. Let's place it in the common directory. So I'm going to TCP underscore KProbe hyphen common, I believe. Yep. And in here, we're going to create a sock.rs, which will hold all of this. And as for the generate command, it's going to be a socket and a sock common. I believe that's what they're called. Let's check once again. I think it's called sock, right? Yes, it's a sock. Right, we've got a sock and we've got a sock underscore common. So let's do that. Great. So what this is doing behind the scenes is it's automatically generating all of the serialization. So instead of us having to manually add the repr C along with each of the fields and manually lay out the essentially the map of the structure, it's going to do that for us. So let's get rid of all of this because we don't need that anymore. And we can take a look at what it has generated for us. So if I go into the common directory and I go into lib.rs, oh, sorry, it actually created it here. Let me delete this. ALL TCP common. This is supposed to be in the source directory. So let's do that, src. And while that generates, let's take a look at the source directory. So as you can see, it's generated a lot of code for us. What's important for us here is if I take a look at, if I do a command F, okay, let it index all of this first. It's going to take some time. Okay, so now that it's done in indexing, I can take a look at the sock.rs. And as you can see, it's got a structure which with a repr C, and it's got all of the data that we need. It's essentially serialized or rather defined in Rust for us the entire data structure that will be stored in memory. So let's move forward with this. We're going to have to let's do that. It's going to be pub mod sock. Along with that, we need to add a couple directives so that Rust does not yell at us. Let's just copy that from here and we're going to paste this. Great. So now that we've got this going for us, we can refer to this in the eBPF application. I'm going to close all of the other files. So let's do that. Close other tabs. Yes. Great. So our sock pointer is going to be a sock, and this is also going to be sock. Let's import this. Great. So Rust is going to bring the sock. It's essentially going to refer to the memory location, going to convert that into a Rust data structure. It's going to bring that API. Essentially, it's going to expose all of that to us. Now let's try to reference some of the elements in here. Okay, we've got a couple problems. So if we take a look at the SK common structure, since in the definition it's a union, in the definition on the documentation, if we take a look at the first element, let's see, sock common. Right. So since the first element is actually a union of an adder pair as well as this structure, Bindgen doesn't really know what we were trying to achieve. So if we look into the definition of this, we've got the adder pair and we've got anonymous Bindgen definitions for the SKC adder as well as the receive adder. So what we're essentially going to do is we're going to go into the uh, we're going to go into this element which is the union, and then we're going to extract we're going to extract what we want from the Bindgen ty1 structure. So what does that really mean in practice? Let's take a look at that. In here we're going to refer to Bindgen anon 1, and in here, whoa, okay, let's go back in here and going to go into this right here, and in here we've got the skc adder. So let's just make it skc underscore adder equals, you know what, I'm going to call it sk common equals this, and then when we want the destination adder, it's going to be a skc underscore adder equals sk underscore common dot, and then I can paste what I had copied earlier. So as you can see, the compiler is yelling at me. That's because since the Bindgen field was a union, it doesn't really know the whole unpacking operation in here is unsafe. So it's going to ask me to wrap this in an unsafe block. I'm going to do just that, unsafe, and we've got that going for ourselves. Let's get rid of this. As for the port as well, we're going to do the same thing. let skc underscore dport, and that is going to be sk common dot. Again, I believe it goes into the bindgen. Let's take a look. In here we've got the bindgen. This is the adder pair. Let's go into this one. These are the hashes. In here we've got the port pair, and we've got the destination port here. Cool. So that's in the third anonymous bindgen. So we're going to have to go in here into the third bindgen, and we've got the skc port here. Cool. So now we've got our port. Actually, let's get rid of this. Cool. It's yelling at me because this is a big endian 16. I have to convert this into a U16. I believe that's how it's done. All right, let's get rid of this. Cool. The last thing it's expecting is the family. So I believe that can also be achieved from sockcommon.skc family. Great. So I think we have all of our details here. Let's try running this application. And it's going to throw a lot of errors. That's because I'll let you know why. So this bindgen is generated by II eBPF, and since we added this to our uh, common crate, the common crate doesn't really have any dependencies on II. It does not depend on II yet, so we're going to have to add that. Let's do that real quick, and now it should build properly. That didn't work. Right. This is something I completely missed, but I wanted to make this a point. So if we take a look at the error that we're getting right now, it says that the TCP probe function is exceeding its stack limit. Now, this is where we come into the problem that I had mentioned in the first video, where the maximum stack size that you can achieve in eBPF is 512 bytes. So this structure, the socket structure, is huge. If you take a look at the definition, it's massive. So it's going over the 512 bytes of the stack that we're allowed to have. The way we can get around that is if we just skip actually deserializing the sock structure, because if we look into the sock structure, let me go in here. The sock structure is massive, but most of the data that we need is actually in the sock common structure, which is not that big. So let's just skip all of this. Let's just make it serialize the sock common structure. So we're going to do that by, let's see, let's get rid of the sock pointer and that. Let's get change this to sock common. Wait, let's create a pointer for it first. Let skc underscore ptr. This is going to be a star const common. Oh, let's see. That is going to be our ctx.arg 0. The reason I can get away with referring to the same place as sock common as well as sock is because since sock common is the first structure in the socket structure, so both of them are going to start at the 0 byte. If this was, let's say, the third or the fourth argument, then I would have to add an offset onto the pointer as well. Let's just do IU32 and cool. Now that we've got this, it's going to read the skc pointer, and we will have let sock common equals skc. This is our sock common. Great. Let's just make it sk common. Cool. So everything works fine, should work fine. Now we've got all of the compiler errors sorted, and let's take a look at our application. Why is this highlighted with red? I think it's just not updating yet. Let's see. Okay, let's open a terminal window and perform a curl. Cool. Again, we've not actually started processing the difference between IPv4 and IPv6 yet, so this is expected, but let's take a look at google.com as well. Awesome. So it has resolved, it has given me the output for google.com as well. Just to be on the safe side, let's do a -6 of this so that it goes over IPv6. Cool. Let's see. Now we need to handle the fact that our families, the IP family might be different, and we need to handle both of those separately. So let's do a match on that real quick. It's going to be a match on skcommon.skc underscore family. Cool. So in case it's a 2, we're going to do something. And if it's a 10, we're going to do something else. Let's just cut this for now. Cool. And of course, it's going to yell at us because of an incomplete match statement. So let's add one for that as well. Cool. We're going to keep this the same as we did earlier for IPv4. The difference now being in the case of an IPv6 address, we are going to handle the fact that it's an IPv6 address. Let's just copy this over for now. We're going to do a, let's see, deadder in 6, I believe. I am not sure what it's called. Let's go all the way back up into our SK common. And let's see. SKC v6 deadder is what it's called. So we're going to call it SKC v. Whoa. Okay. Let SKC. Oh, okay. So I cannot actually call it SKC here. Let's just do a let SKC v6 deadder equals sk.common v6 deadder. I believe that's it actually, so I don't need to do all of this. This is not in a union, so I don't need any unsafe blocks in here. The port and everything else should be fine. Why is it yelling at me? Let's see. That's because it's an inet address. I need to convert this into one of these. Okay. So it's going to be an in6 underscore u dot in6 underscore u. And then in here, we're going to extract the u6 underscore adder 8 dot u6 underscore adder 8. And yes, this needs an unsafe block all the way through. Cool. So let's clear our logs real quick and let's run this again. And we're going to check if it logs everything properly. In case of an IPv6 call, I'm getting a proper IPv6 address for the destination. And in case of an IPv4 call, I'm getting a proper address here as well. The port works fine as well because if I use HTTPS, I'm getting just what I expect in here as well. So cool. I think we've dealt with the major part of this tutorial. Let's do a quick recap. So in the beginning, we just had a normal logger. Whenever the connect method is called, just produce that log. Then we looked into getting the actual reference to the pointer, getting the exact pointer that was passed into the kernel. Along with that, passed into the function. Then we looked into calling the BPF read kernel method to extract the raw data that was present in kernel memory referred to by that pointer. Once we got done with that, we took a look into how we can use Bindgen to generate all of the data structures that the kernel needs instead of manually writing all of those ourselves. And there are use cases for both of them. Like if we were just making something that had IPv4 support, no real support for IPv6, I think manually writing those representations yourself is not a bad idea. However, when those structures get really huge, it gets kind of tedious to write all of them manually, and any errors in those are not really reported at compile time. So there are use cases for both approaches. Anywho, so once we got done with that, we actually extracted details that we needed out of those data structures. So we got the family of the socket, we got the port, the destination port address, we got the IP address and everything. So this has been a lot of progress for this video. In the next one, we'll take a look at uprobes along with a little bit about perf events or hash maps, depending on if time permits. And we're going to take a look at sharing data between the kernel space and the user space. So far, all we've been doing is logging. But what if we need to programmatically send data to user space for whatever reason, for whatever processing that might be done in user space? So we're going to take a look at that in the upcoming videos. Anywho, I hope you enjoyed this video. Thanks a lot for watching, and I hope to see you soon. Bye bye.